Welcome to Team 16's final video presentation. We are working on using deep learning for limit order book analysis. There's inherent value in being able to predict aspects of the limit order book for high-frequency traders. If a trader could predict the bid and ask levels at T+1, there's the possibility for arbitrage, as he could fulfill an order at time T knowing he'd be able to exit the position profitably at time T+1. A limit order book is a record of outstanding limit orders maintained by the security specialist who works at the exchange. A limit order is a type of order to buy or sell a security at a specific price or better. A buy limit order is an order to buy at a present price or lower, while a sell limit order is an order to sell a security at a pre-specified price or higher. The data used is the benchmark high-frequency limit order book for mid-price prediction. It contains tick data for 5 NASDAQ Nordic stocks over 10 trading days, yielding roughly 4 million samples. For each point in time and for each stock, the data will have 10 levels on each side of the current bid-ask spread. This includes the 10 price levels above the ask with quoted volume and 10 price levels quoted below the bid with quoted volume. These levels represent the collection of all open orders at a point in time for a stock. The goal is to use these supply and demand levels to improve bid-ask spread midpoint price prediction at high frequency levels to find an exploitable source of alpha. All data is provided in 3 different normalization methods: z-score, min-max, and decimal precision normalization. We use a CNN LSTM hybrid architecture to forecast the next step mid-price. The motivation for utilizing this architecture is that it will capture both the spatial and temporal dependencies of the limit order book. The initial convolutional layers capture dependencies between different levels of the order book and their respective volumes. An inception module with various kernel sizes is then used. We pass the resulting feature set to 2 LSTM layers which process temporal dependencies across the look-back window of 100 samples. We measure our results in terms of model skill. Skill can be defined as 1 minus model MSE over baseline MSE. In this way, a perfect model will have a skill metric of 1, and a model in which the baseline outperforms has a negative skill value. To cross-validate our out-of-sample performance, we use 11 rolling windows divided into a validation, train, and test set. The ratio of validation to train to test set size is 1/6, 2/3, and 1/6. The window lengths were 1/6 the total length of the data. We trained all models with a minimum number of epochs set at 75 and trained until the training MAPE was at or below 0.14. Average skill out of sample was 0.692, which indicates that our model outperformed the baseline model significantly. This concludes our presentation. Thank you for your time.